This is the 2024 deferred exam paper. It's paper 2 and we're on section B, and this is question 7, which is a question on statistics. And we'll see later as we go on, in particular it's on inferential statistics. So the first part of question 7, part A, we're told basically that there are trees in a forest and they follow a bell curve, basically the heights of the trees. So this is the bell curve here. I've drawn a quick sketch, and in other words, they're normally distributed, same thing as bell curve. And we're told the mean height of the trees is 360, so that's bang in the middle there. And there's a standard dev of 27. So I'll just write those two things down. The mean is 360 and the standard dev is 27. Now, a quick tip about these questions in the exam. I like to think that this sketch makes things easier. So I draw a quick sketch of a bell curve and I draw 3 lines, which I call the X line, the Z line and the P line. And the X line, you put the actual heights of the trees on that line. So the mean is in the middle. It looks like in this question we're interested in 2 particular heights. We want the trees between 330 and 390. So put those on your X line. And as you can see, that's 30 down from the mean, that's 30 up from the mean. So there's symmetry here as well. Okay, and now find probability that the heights are between here and here. So the probability I assign to the P line here, as I call it. So we can work out the probabilities on this P line. Now my method here is what I call line hopping. We have to get down to the P line and find out the values of the probabilities. And to do that, you must hop from the X to the Z. So I call this line hopping. You hop from X to Z and then you go from Z to P. So in other words, you have to go through Z first, Z scores first, before you get to P. How would you go from the X line to the Z line? Well, there's a formula. It's in the tables. Z is simply X minus mu over sigma. What Z measures is basically how far away you are from the mean. So it's your tree height minus the mean tree height, how far away you are, measured in standard dev. So your unit of measurement is standard devs here. That's why standard dev is below the line. Obviously, if you're on the middle, your Z score is 0. You know, you have a Z score of 0 because you're 0 away from standard devs away from the mean at that point. So keep that in mind for interpreting the diagram. So it's just a formula to go from here to here, as I said, Z X minus mu over sigma. So let's do that up here. We're interested in the trees of height 390 first. So 390 minus the mean, 360 over 27. You get 1.11 on the calculator. So that's your Z score. That's how far away you are from the mean. So that's 0, as I said here. Now it stands to reason, because of the symmetry, that this must be minus 1.11 if that's 0, the 330. So that's a shortcut, just put down the minus 1.11 straight away. And we can now go from Z scores to the P line here. I won't call them P scores yet because that's technically something different. So we can go from Z to P using the tables. You just look up the Z score and it gives you a corresponding P score basically in the tables. If we look up 1.11 in the tables, we get 0.8665. So we finally have the value of the probability at this point here. What does that actually mean in terms of the trees? It means basically if you get 0.8665, that really roughly 86%, 87% of the trees are below this height. That's all it means. So it's always what's below that point. That's what it gives you. However, I'm not quite interested in that. I want what's between here and here. So again, we can now use symmetry of the graph. So what we do here to find this point down here, now the Z scores only work from here up in the tables, from 0 upward. They don't give you negative values. So how do you get from here to here if it's not in the tables? Well, it's just a symmetry. If there's 86, we'll just say if it's 86% below this point, that means there's, what's the remainder? 100 minus that above. Or if you want to do it in probabilities, it's 1 minus that number is above. So whatever that probability is, 1 minus that is above it. And 1 minus that, I work it out down here and I get 0.1335. And of course, by symmetry, the proportion that's above that point is the same as the proportion that's below that point. So there's my 0.1335. I now know that basically 13% of the trees roughly are below this height. So if I know that 86% roughly are below this height and 13% are below that height, What's in between? We'll just subtract your percentages, or your probabilities in this case. So it's 0.8665 minus 0.1335, and the answer is 0.733. In other words, approximately 73.3% of all the trees are between those two heights. On to the next part. Now, the shortest 5% of trees are not sent to the factory. So the whole idea here is you're harvesting trees, and if they're not tall enough, they're not sent to the factory, basically. What's the minimum height? So got to be careful with language here, not as in bold, because he wants to draw attention to the fact that they're not sent to the factory. But what we're interested in is the ones that are sent to the factory. What should the height be so that it is sent to the factory? The other thing that's important here is, if you look at the big picture, in terms of line hopping, what's actually happening in the question overall. Up there we were given the X score, the height of the trees, and we had to get the P score. So we hopped forward, as I call it, here to here and here to here. We hopped from the X line to the Z line to the P line. We were given the X, we were looking for the probability. As it says there, find probability. Now this is the opposite. If you read the question carefully, you'll see that, look, he's the shortest 5%. In other words, that's not the probability. He's given us the 0.05. So we're starting on this line. And we want to find out the height of the tree. In other words, the X value. What is the minute? So this is going into reverse, basically. We're starting here, and we want to hop backwards up to get the X value right there. So let's be clear on what we're being asked. We're being asked basically to hop from here to here to here. And then the rest of the question should be a bit easier. Okay, how do you hop backwards is the next question. Again, first of all, we got a problem, because to go from this line to this line is the tables. And the tables only work from 0 up, not from 0 down. So again, we're in trouble with the 0.05. Yet again, we use symmetry. If it's 0.05 on this side, well, it's 1 minus that, which is 0.95 on this side. We're going to use the 0.95 on this side. We'll hop backwards. Now look up the tables, but bear in mind we're going backwards this time, so I've it done out here. Normally with z-scores, if you're going forward, the z-score is there if you're hopping down, and you hop down, you have the z-score here, like 1.64 for example, and this is the corresponding P probability. Now we're going backwards, so we're now starting in here, and we're working out to the z-score here. So watch out for that. Now, for 0.95, what is the answer? For that probability to work backwards? Well, that's what I'm just trying to do here. If you look around for 0.95 in here in the probabilities, it's not there. The closest we can get is 0.9495 below, 0.9505 above. As it happens, it's exactly in the middle, 0.95. So which one of these do we use is now the big question. And if you read the context of the question, that's where this comes in, the fact that we're looking for the ones that are sent to the factory. What's the mean height that is sent to the factory? Well, if you had the 0.95 exactly, for example, the 0.95 exactly, that's kind of bang in the middle here. That's the cutoff point. Okay, so the cutoff point, if you kind of transferred the diagram up here, the cutoff point would be on this side, and by symmetry on this side as well. Now, we want the ones that are kept. So if you look at the cutoff point, we want the ones that are just to the right of it. If you're talking about 0.05, if you could adjust to this side slightly. Or by symmetry, it's just below this point here. So that's, in other words, just below the 0.95. So that's why we go below. We're going to pick the below one because that's the other trees we want to keep are the ones that are between the two boundaries here. So we're going to go with this one. So basically, to make a long story short, when you go backwards from 0.95, you pick this one, the lower one, and that gives you a z-score going backwards of 1.64. And that's what we're dealing with right there. We hop back to 1.64. Now, to hop from here to here, you use the formula. Just use the formula backwards, basically. So we have the z-score now, so fill it in. We're looking for the x-score. That's the whole point. So it's the x-score we don't have minus the mean we do have over standard dev, which we do have as well. And you can work that out now, and you can work backwards to get x from the formula, and you'll find out that x is 404.28. There it is right there. Now, of course, this is the point we're after, because we're talking about the shortest 5% of trees. So this is the one we're really after. But again, by symmetry, we can see that if you just subtract this minus this to get the gap, and then get the same gap again, you'll arrive down here. So you just take your 404.28, you subtract your 360 to get this gap here, and then you go again, subtract, and you'll end up here. So it's 44.28 is the gap. Subtract that again from 360, and you're down to this point here, which is 315.72, and that's the magic number. That's the number, that's the height, that's the minimum height of trees that we'd accept for the factory. 315.72. On to the next part. So this is the whole concept of hypothesis testing. So the null hypothesis, we're making a statement or a claim, and the claim that we're making is that the mean height of trees is 360 centimeters. What's the opposite to that? Basically the alternative hypothesis, well, that the mean height is not the mean height of trees in the forest. Okay, we'll just read this carefully. I think I might have made a typo there. So the mean height of the trees is 360. So the alternative obviously is that the mean height of the trees is not 360. So just correct that there. That's a typo. It's not 360. Okay, so the calculation. Now, this is sampling. So the whole idea of sampling is you take a sample, a small sample of trees, and whatever you find out for that sample, kind of you try to infer or predict all the trees based on that. Basically, that's the idea. So we're given all these numbers, and when you're talking about samples, you always use this set formula. It's different to the previous one. And when there's a sample involved, you have to use this formula here. So what you do is you fill in x bar, which is the sample mean. So a good technique is to label them all here as you're going along. So the mean height of the sample is 350. So you have a small sample of trees, and the mean in your sample is 350. The standard dev is the same as before. It's 27. And the mean for the whole population of trees, so basically all the trees in the forest, the mean is supposed to be 360. And in your sample it's 350. So you fill in those two, and you divide by 27 over the root of your sample size, n, which again you label that up here, n is 100 trees. And you get minus 3.7. What does that minus 3.7 tells us? That's basically how far away we are from the mean. And we're way out. I mean, if you look at the in terms of Z scores on the Z line, you have to be between minus 1.96 and plus 1.96 to be within what we call the 95% confidence interval. We're way outside it. So therefore, the way we say that is we reject the null hypothesis. Now, the reason for your conclusion is simply because we're way outside. Z is minus 3.7, and that's way beyond what we expect. Minus 1.96. We're on to part C. Now, this is a question on sample proportions. So in the previous part there, we basically had a sample of trees from the overall population, and we were getting the sample mean. Now we have a sample from the overall population, and we're getting a sample proportion. So the proportion of trees that have become infected with the disease. So it's a slightly different question. And there's a different formula for that, of course. And the formula goes like this. The proportion, first of all, get the proportion of trees we're talking about. 48 out of 160 are infected. We call that p hat. So 48 out of 160. So the proportion is 0.3 if you work it out. So 0.3 of all your, 30% of all your trees are infected with this disease. That's in your sample, don't forget. Now, we want to use that sample to make a prediction of the infection level in the whole population of trees. So what do? We fill in this formula. Again, you have to learn this formula. It's not in the tables, so you have to learn it off. So this is what's called the margin of error. On either side, what are you going to accept, plus or minus on either side? So this is the minus, this is the plus, on either side of the p hat, which is in the middle. So it's 0.3 plus or minus 1.96. You fill in your 0.3. 1 minus 0.3 is 0.7. Over 160, which is the sample size, and you get this. And you get a lower limit and an upper limit when you work it out, 0.229 and 0.371. So what we're saying is 95% of what you call it. We're 95% confident that the proportion of trees infected is between 0.229 and 0.371. Okay, so that's p hat. That's what we were asked. Now, the last part of it is simply, what does all this mean? I mean, what's the meaning of what we just worked out? What does it mean? Always in these questions, the whole point is you're kind of working blindly. You've got this sample that you're working with, and you're doing your best with the sample, and you're kind of working blindly. You don't know what the right answer is for all the trees, but you're hoping that the answer you get for the sample is going to be accurate to predict what's happening with all the trees. So what it actually means, what you've just worked out in your sample is, we're 95% confident that the population proportion, in other words, in all the trees, that the amount of trees infected is between 0.229 and 0.371. That's what this is all about, inferring or making a prediction about all the trees in the population based on the sample that you have. Okay. And the last part of the question is this. It's kind of testing if you understand the concept of standard deviation, what it really means, as opposed to working blindly with something. In plain English, what standard deviation measures is how spread out numbers are. You know, the more spread out they are in a list of numbers, the more the standard deviation, basically. So if you've got a bell curve, for example, your numbers are spread out here, for example, between here and here. The mean is 360, but that's the spread of numbers that you can be dealing with. And most numbers are in around 360 because that's the mean. But as you trail off on either side, you get some other numbers down to whatever this number is here and here. Now we're asked to draw a new curve that has the same spread, but with a mean of 350. So it's basically a matter of moving the whole bell curve to the left slightly so that it lines up with 350 in the middle as opposed to 360. And that's because, again, it's the same spread, so it should have the same rough shape. It's just the same bell shape. It's just the same spread. It's spread out by the same amount. It's just centered around a different mean, which is 350. Okay, and the last part then, the diagram shows the same normal curve as above with a mean of 360. Okay, so this is the same original bell curve as what he's saying, with a mean of 360 still. Now imagine you have a smaller standard dev, in other words, a smaller spread. So they're tighter, they're more bunched together, basically, the numbers. So what would that look like? Well, a tighter spread, first of all, obviously the tails come in. It's tighter now, it's only between this number and this number, for example. We can draw anyone we like within reason. So I just picked this kind of a spread here. Once it's narrower, that's all that matters. Now, of course, if your numbers are more tightly bunched, let's take the extreme case. Imagine it was marks in an exam and the average was 70. And my students got between 40 and 100 or something. That's a big spread. But if I now make the same average 70 still, but spread between 69, in an extreme case, between 69 and 71, they're really bunched between 69, 70 and 71. If it's the same number of students, that means there's far more students on the mean getting 70 than there was. So there's two things that happen here. It gets narrower, they're more bunched together, but because they're bunched together, there's now more of them on getting the mean mark. So that's why you have to show that this goes up as well, in your standard deviation curve, or your bell curve, as I should say. And that's it. That's the end of that question.